Okay, so I want to give you a little bit more like intuitive understanding of what this effectiveness means, and maybe how like NTU and effectiveness relate to each other. So let's think about a situation where we have a capacitance ratio that's not equal to 1. So let's maybe plot out like temperature as a function of position again. So this is X, this is T. And let's maybe pick a hot and a cold. So like hot, cold down here. We'll pick blue for cold. So let's say cold looks like this. And let's say hot looks something like this. So it's an unbalanced heat exchanger. Hot, cold. And what can we like observe about this, I guess? The first thing is going to be, which of these two has a lower capacitance rate? Is it the hot or the cold? Remember, capacitance rate is m dot times Cp. They're both absorbing the or transferring the same amount of heat. So which one has the lower capacitance rate? Any guesses? No? All right. So the one with the lower capacitance rate is the one that can sort of absorb less heat for a given amount of temperature. Right? So if I were to increase the temperature 1 degree Kelvin, but I have a very low capacitance rate, that means that I'd better have like a high mass flow rate that goes with it. Right? So say that sort of backwards. What I mean is like this fluid here is the one that has the lower capacitance rate. So it can sort of, for a given increase in temperature, absorb less heat, or vice versa, right? So this is C dot min here. So you're always looking for the one that changes its temperature the most. That is the one that has the lowest capacitance rate. So then how does this relate to effectiveness? Well, okay, let's map this out a little bit. So let's say here, kind of map it over this way. We have these 4 temperatures that we're worried about. So this is TH in, this is TC out, this is TH out, and this is TC in. So delta T max, like the maximum amount of delta T in the system, oops, down here, is this, right? This is delta T max. So what is, what's the delta T that corresponds with the minimum capacitance rate? Well, that's going to be the delta T associated with the C dot min, right? And that in this case is the cold side. So it would be this one here. So this is delta T min, or C dot min. Okay, so what the effectiveness is telling us is basically how much heat is being transferred compared to the total amount that's possible. Well, in terms of temperature, it's basically delta T C dot min over delta T max. So effectiveness here is delta T C dot min over delta T max. So if you wanted to figure out what the effectiveness was, a good surrogate for that, aside from doing the heat transfer analysis and all that, is to look at the temperature stream that changes the most, that delta T, over the maximum possible delta T. All right? Another way to convince yourself of this is like what would happen in the case where like the heat exchanger was infinitely long. Basically, this line would converge right up to that red point. So those two temperatures would become the same temperature difference. And in that case, now you have an effectiveness of 1, right? And that's kind of where that makes sense. Okay. Let's see, second to last thing. I think we have time here. So I wanted to kind of map out what happens, how the relationship between NTU relates to this stuff. So on the scale here, what did I skip? Yeah, here we go. So on the scale here, I've got NTU. So again, this could be a number from 0 to infinity. And let's say over here, I'm going to plot out, this is a value of 1, this is a value of 0, and this is my effectiveness. So if I were to plot like the effectiveness, the effectiveness of the heat exchanger as a function of NTU, how would we expect this to go? Well, if NTU is a surrogate for size, and I make this heat exchanger really, really small physically, or because I make like the C dots super big, NTU basically goes to 0, right? If that's the case, I'm throwing a bunch of mass flow rate through a really, really small heat exchanger. I get very little heat transfer. Effectiveness becomes 0. So if I were to sketch that out, it sort of starts at the 0, 0 point down here. Now as I increase NTU, I'm going to find that there's a pretty quick response to effectiveness. But there's a certain point at which I could keep adding more and more and more material, but it's not going to change my result. Right? I've already sort of transferred all the heat that's to transfer. So if you map this out, it's going to maybe look something like this. Right? So why is this not going to 1? Well, I suppose if you went far enough out, it would. So maybe that NTU is, 10 or 20 or 50 or something like that. So this in this case, might eventually converge to 1. In fact, I might have even drawn it a little too low if you go look in the book. But this, let's say this is for a capacitance ratio equal to 1. So it's a balanced heat exchanger. Now, if we went back and did the same kind of thing for a situation where there's, say, like one mass flow or one capacitance rate that's a lot higher than the other, then what would we expect? Well, because, again, we're being limited by that minimum capacitance ratio, or the capacitance rate, you're going to start to see that, like that just by the definition of effectiveness, we converge much sooner. So what you'd look at is something like this. So it might look like this, and then like this, and so on. And eventually, in this direction, we're saying this is CR as it goes to 0, right? So maybe up here, this is actually CR equals 0. So you're sort of moving this curve up, right? But again, like this is, for any generic counterflow heat exchanger, like you can describe the performance. If you happen to know NTU, you can compute the effectiveness this way. Okay, so that's kind of the relationship there. Sorry, this should be what happens when CR is less than 1 up there. So then the other way of looking at this is in terms of like a parallel flow. So this is for a counterflow. Let me just write that out. Counterflow. What happens for a parallel flow? All right, so for parallel flow, again, we have, down here we have NTU. Here we have effectiveness. This is 1, this is 0. At 0, I'm going to start off at the 0, 0 point. But then the question is, like, how does stuff kind of progress? So maybe let's think about an example where the flows are balanced, right? Capacitance rate is equal on both sides. CR equals 1. If you have an infinitely long heat exchanger, what are the temperatures going to do? Right? You have hot coming in, cold coming in. They're going to converge in the middle, right? And in terms of effectiveness, what does that mean? Well, you're still defining it by the hottest and the coldest temperature, but you're only getting halfway, even for an infinitely long heat exchanger. So for a CR of 1, it's going to look something like this. And so this is my 0.5 value. What happens if capacitance ratio is less than 1? That means, one fluid stream is changing a lot more in temperature. Well, actually, you could kind of sketch it out, right? So like if it looked like this, maybe you have one fluid stream that's only changing temperature a little bit on the hot side, and then another fluid that's changing temperature quite a bit on this side, right? This is still a parallel flow heat exchanger. It's just that one is changing temperature a lot more than the other. In that example that I drew, what is the effectiveness? It's starting to approach 1 again. So as you draw this family of curves out, it's going to kind of look like this. Where this is 1 up here. So this is now CR less than 1. Maybe over here, this is CR equals 0. So I drew it a little bit sloppy, but like you get the idea, right? This family of curves is moving up. The really interesting thing, the last thing I'll say, is that look at this CR, right, for parallel flow, and compare that to, let me just scroll up, this CR for counterflow. They're basically the same thing, right? And if, in fact, in the limit where CR is 0, and it can never really get there, but in that limit, you have the same exact solution. So what that means is, let's say you go design a heat exchanger, and you compute the fact that CR is equal to 0. And your boss says, no, it's really important to do counterflow because Mike said it was really important all the time. Well, you can come back and say, well, no, I was at the lecture that he said that it doesn't matter because parallel flow and counterflow converge to the same solution. So it doesn't matter which way you plumb it, right? If you have a capacitance ratio that's really low, it doesn't matter. You can plumb it in any way you want, parallel counterflow, and it's not going to change the result, okay? Any last questions on that before we? Okay, now everybody wants to go. Okay, well, have a nice break. We'll see you all on Monday.